Okay, so a question was raised about the exams in class and the final exams. So you have two finals and two midterm in class exams, which are basically take home exam. So your let's say you take home. So those are worth maximum 25% of your final of course grade. And then you have your final one, and you have a final two. And this is 75% of your course grade. So let's take this up. Say, for example, if final one is higher than your take homes, then your final is 100% of your course grade. Okay? So, say, for example, your final one is lower than you take home, then this is 75%. Plus 25% from here. So, okay. Say, for example, if this is, say, a B or so, and you're not satisfied, you can opt in to make the final two exam. And then the same principle applies. If your final two is higher than your take home, then it's 100% of your grade. And if your final two is lower than you take home, then it's again 75% plus 25%. And if you still fail, then you fail. Then I see you in the fall semester as well. So, say for example, you got a B here, you got a C here. So you just had a bad day. Then this still is valid. So, in theory, your second final cannot hurt you. But I would do ask, like, if you know, for example, if you're gonna do this exam, just take it seriously. So don't just show up and do the exam because it just gives me extra work. So if you're not gonna take it seriously, if you're like, I'm satisfied with B, just don't do it. Saves me my time. But you're free to do it. So I cannot stop you, I won't stop you, but I just ask for you. If you're gonna do it, make sure you study for it and you take it seriously. So it's not something just adding work for me.
It's a very unique grading system.
Yeah, it is. It's definitely something that you don't often see here. And the reason is, I really don't like homework being part of your final because I think homework should be something that you do on yourself to make sure that you learn the topic in a proper manner. And the same thing, like, why I don't do just one final. I think here in the US, because you fail and you have to wait a whole semester, I don't think that's fair. So I think always should have, everybody can have a bad day. I've had bad days that I know a topic and just go into the exam and just have a bad day and I fail. So I don't think that's fair either. So I think in this way, you can get something of the homework. So it gives you incentives of doing the homework or to take home exams and doing well on those. And at the same time, if you have a bad day during the final, you always have some catch up. And sometimes you didn't get it, but you because the final will be a comprehensive all the topics. So if you can showcase that on the final you understand all the topics, I don't think the take home should bring you down just because back then you didn't understand it fully or something like that. So I think this helps is in the benefit of all the students. And gives you incentive to do the homeworks, and also doesn't punish you if you have like just a bad day.
That's a very good reasoning. I like it.
Okay. So for today we're gonna continue doing some problems. I'll focus on one shear and one torsion. I'm gonna focus with the torsion, so I would definitely wanna get that in as well. And the shear problem, worst case scenario, if we don't finish it, yes, sorry.
Will the final be in class or online?
I haven't decided. Originally, it should be in class. That's my preferred. Given the situation, given, say, the university sent out that everybody should be back in school, but there's still people not vaccinated and stuff like that. So I don't want to risk anyone's health. So it might be that's again a take-home exam. If it is a take-home exam, it will be limited to 6 hours, so it will be a bit more time pressure though. And it probably it will be 6 hours in which the class fits. So it will probably be on Tuesday or Thursday, say noon to 6 p.m., something like that, or oh no, actually we start at 11:40, so we'll probably start at 11:30 till 5:30. So you have the class hours, so you technically should have at least 1 hour and 50 minutes to do it, plus lunch, so you give you some freedom. And I think this will be definitely in the week of, I think it's end of class is May, right? So May 4th or so. So probably be one of them will be the week before. And I think in those weeks, anyways, less lectures going on, so you should have plenty of time to do it. Okay. But I'll send out an email discussing a couple of things, a couple of options, and see what the feedback is from you guys, and then I'll decide. With that as well, I sent out another email as well, if you guys can fill in. If you're doing a bachelor's of mechanical or aerospace, is this an elective or core course? Are you doing a Master of Science or Master of Engineering? I sent out an email with a link in it, so if that link doesn't work, just let me know. And if you can fill that in, will help me out and will help the university out, because as you all know, we are currently trying to get the whole bachelor's accredited, the aerospace engineering course, so it's useful to have these numbers available for the university. With that said, let's go into our problem solving again. Like I said, I'm going to start with a torsion problem, and then we go, the remainder of the time, we're going to our shear flow problem again. So let's go for our Z section again. And in this case, this is 10 millimeters. This is 15 millimeters. And the height is 30. You see? Yeah, you can see. Perfect. You have a couple of things given. We know there's a torque acting upon this section of 100 Newton meter. So that's just 100 times 10 to the power of 3 Newton millimeter. And that's one thing we always suggest is whenever you have given problems or variables, stick to one unit. I think millimeters is always the best option to go for, especially shear flow problems, unless it's 1,000, 2,300. Then go for centimeters or meters in worst case scenario. But yeah, this is what I would do. So the question is, let's write that here. The question is, determine the shear modulus of the beam. So we don't calculate any shear flow and etc. We basically have to calculate what the shear modulus is, and that's G. And it will pop up in one of the equations, so we can isolate that and determine it. So a couple of things are given. First of all, thickness is 1.3 millimeters everywhere. And we also have given, if we apply that 100 Newton meter torque to it, and the beam has length L is 0.7 meters, it rotates a theta of 1 degree. Okay. So this is what we have to do. So and a couple of steps that we can solve this problem. First of all, we are given, the question is basically determine the shear modulus. So we know a couple of things. We know that torsion is equal to the shear modulus multiplied by the torsion rigidity multiplied by the theta dc. And this is our rate of twist. And what is rate of twist is rate per rotation per unit length, or rotation per meter. Okay. So If you look at the equation that basically comprehends this problem, we have torsion, we have shear modulus, shear rigidity, torsion rigidity, and the theta dc. The theta dc we can determine basically by the length and the degree of rotation. G is the unknown. The shear, torsion rigidity we can determine. That's equal to the summation of st cubed over 3. The torsion is already provided, 110 to the minus 3 Newton millimeter. Shears are unknown, and the theta dc we have to determine. The theta dc in this case will be 1 degree of rotation over the length, and this is 1.429 degrees per meter. And we have to go, of course, in our standard unit. This is given in radians, or the theta dc is given, it should be divided in radians. So we have to multiply that by pi over 180 in order to get the correct units. So this gives us 0.025 meters or radians per meter. And if we are consistent, if we go to millimeters, we get 2 times 2.5 10 to minus 5 radians per millimeter. So basically what we have is one equation, one unknown. We can solve for it. Very simple. So let's also fill in our torsion rigidity. That's J. There's an open section thin wall beam. So it's basically the summation of ST times 3. S is our segment, T is our thickness of the segments, over 3 is just over 3. So let's fill that in. So we have our segment 1, that's 15, plus, I'm going to isolate T, by the way, since T is everywhere the same. But if it would not be the case, then you just multiply by T by the corresponding segment. So 15 plus 30 plus 10, and that's multiplied by 1.5 times to the power of 3. And if we fill that in, we get 40.28 millimeter to the power of 4. Is that correct? Yeah.
Should be 1.3 instead of 1.5.
Which are you talking about?
The thickness is 1.3 millimeters everywhere, but you put 1.5.
Oh, yeah, you're correct. I don't know why. 1.3.
But the answer is still correct, 40.
Yeah. Yes, it's 1.3 my work notes. So basically what we have now here, going from right to left, we now have our torsion 10.3 is equal, let's rewrite this a bit. So we have this equation, so we isolate G. So G is equal to T over J times the theta dz. So that's equal to 100 10 minus 3 over 40.28 multiplied by 2.5 10 to minus 5. And this will give us a number of, let me see, yeah, 9.9 10 to the power 7. And since we are working in millimeters and newtons, this gives us Newton per millimeter squared. So there's actually a follow-up part of this question was, does this make sense? So we have 9.9 10 to the power 7, which means this is Newton millimeter squared is megapascal, so this is 9.9 10 to the power 7 megapascal. So if you go to gigapascal, it's 9.9 10 to the power 4 gigapascal. And then you should basically see that this does not make sense. There's no material that has such a high shear modulus. You have to think about like, let me see, did I write down? Yeah. So steel, for example, shear modulus of steel is around 80 megapascals. The shear modulus of aluminum is around 25 megapascals. So if you want to basically design this beam for that kind of load and that kind of rate of twist, it's just not possible. So what you do is basically, what you go from here is, you could plug one of these G's in and basically determine what, for the length and for the torsion, what the rotation angle would be. Basically, you can plug it in and reverse engineer what the rotation angle is, and then you will realize actually with this load again and this length, that would also not make sense, because then the structure would rotate like 7 times. So there are a couple of things where you can do. It's not always as straightforward calculating your shear flow or your stance. It's also think going at, does this make sense? What is it? And giving you that extra step of thinking. So in this case, this would be an exam problem. Part of the point is definitely related in getting this calculation step done. And I would say this is a very simple problem, so I'll probably give a maximum of 5 points. This would be 3 points, and justifying why it's incorrect or correct will be 2 additional points. So it's almost 50% of the problem. So of course, given the problem, some cases you have to, there's a justification at the end, but then the steps going through it takes like a couple of pages, then the distribution of the points will reflect that as well. But always, there will be a next step to it. And I realized actually when making the exam, or trying to make the exam actually, with torsion, they will be somewhat limited because we haven't discussed multi-section problems, and that's where often torsion comes into play as well. So I will ignore that section, so I'll just focus on the torsional problems that we discussed so far in the class, and I don't want to bring up any new problems before the exam as well. So with that said, you can assume that it will be heavily on shear, and there will be just one problem maybe with torsion related to it. So after this lecture, or after this exam, we'll also go into multi-sections. What happens if we actually have say a wind structure and has multiple cells, say cell 1, 2, 3, and then we discuss that, and then torsion will pop up again, and rate of twist will pop up again. But for now, that's basically ignored. Okay, so with that said, let's do another shear flow problem. And in this case, again, we're going to look at, let me see. So the question is, determine the shear flows. Determine the shear flows for the given structure and then we have given certain structure, triangle. This is height h, and this is length d. This length is similar, so this is d as well. And we have a shear force acting on it at this location. So we know, based on geometry, we have a closed problem, a closed section. section shear flow. So we know we have to make a cut to the open section, QS or QB, find QS0, add to get final results. So this will be QB plus QS0. So that's the steps that come into mind, or that should come up immediately into your mind. So that will be our procedure. So okay, let's see. So let's analyze our problem a bit more detail. So we have our solution procedure. So what do we know about our shear flow problem? Well, we know it's symmetric. We have one axis of symmetry. So let's use that. We have no shear force in the x direction given, so we can use that as well. So we know our shear flow problem becomes minus sy over ixx, integral from 0 to s dy ds. So since this is our equation that we can utilize, there's no need to calculate moment of inertia and yy, because it's symmetric, iyx is 0. So let's put it here. Symmetry, ixy 0, no sx given. So that's also an additional observation that we make. So let's calculate the moment of inertia. And in this case, we have our straight section that we can use basically 1/12. And then we have to deal with the sections. Let's give it a couple of names as well, by the way. Let's call this point 1, point 2, and point 3.
Do I need to find the centroid first?
No, because the centroid is with respect to y, and we know that it will lie around the x-axis, so we can easily find. So the centroid will be somewhere here, but since we're not dealing with any y disturbance, we don't need it. So okay, so let's calculate. So 2-3 section, that's easy. That's the 1/12 bh cubed. Also have to define what the thickness is. So thickness is everywhere t. So in this case, it will become 1/12 h cubed t. And we know from our shear moment of inertia lecture is the moment of inertia of ixx of our cross section is equal to the moment of inertia of xx in 2, 3 plus moment of inertia xx in 1, 2 plus moment of inertia of xx in 1, 3. And we also know that moment of inertia in 1, 2 is equal to the moment of inertia in 1, 3, based on symmetry. So we basically have to calculate what 1, 2 is or 1, 3. So let's do that. So 1, 3. And we basically let's go for the integral format, YdA. So there's a formula, and you have to be a bit careful with, again, how the picture is given on the formula sheet, because there's an existing formula that you can basically determine this immediately based on the variables given, so you don't have to do integral format, but I do want to emphasize of actually feeling comfortable doing the integral format. So we have to basically define what a y squared will be. So with that, let's look at the cross section again. So again, we have an we have a geometry, we have a central symmetry, so we can define this as alpha. And if we define this as alpha, then we know that y is equal to, in this case, y is equal to And if we go from S1, so going from this direction, this will be equal to S1 multiplied by sine alpha. So one step is calculating sine alpha, or just going with sine alpha. Another step is, how is sine alpha defined? Well, sine alpha in this case is defined as sine alpha is equal to minus h over 2d. It basically is half h over d, so minus half h over d, and that becomes minus h over 2d. So that's where the 2 comes from. Basically, it's nothing else than this part. So say 2, 4 over 1, 2. So we can plug that into our equation, and then we can do the integral format. So let's do that. And then, of course, our segment bond goes from 0 to s, which goes from 0 to d. So our integration bond, if we fill this in as well, it goes from 0 to d. And then we fill in this equation. So if we do it correctly, we get S1 times sine alpha squared dA. This becomes 0 to d of, now we substitute sine alpha, S1 multiplied by minus h over 2d squared. And the area is nothing else than t times d, ds. If we take a segment on this line, this area, if we blow it up, that's the thickness multiplied by our segment ds that we take out with. So our dA becomes t times ds. So that's a Coulomb transformation that we apply here. So we get t ds1. And then we can basically evaluate this integral. We have a bunch of stuff. And the only thing is a function of S1 is S1. So we can take out this part out of the integral. We get is th cubed over 4d. The minus disappears. And then we get 0 to d s1 squared ds1. So this becomes th cubed squared 4d, and this integral becomes 1/3 s1 to the power 3, evaluated from 0 to d, of course. So if you plug in 0, it's 0. If you plug in d, what we get is th squared d to the power 3 over 1/3 times 1/4, so that's 1/12. And here we have d, so we can basically cancel out 1d, so this becomes d squared, and this d disappears.
So why was the d in the denominator not squared?
It should be. And this becomes here. That's correct. So yeah, there should be a d squared here because we multiply this square sign. No, you're correct. It was a mistake on my side. So now we know the moment of inertia for our cross section. Let's just call that 1xx, ixx. So it's 1/12 h cubed t plus 1/12 h squared t d. And then you can simplify it a bit. Sorry. This is for segment 1, 2, so this must be multiplied by 2 because segment 1, 2, and 1, 3 are the same. So we use that to our advantage. So that's the 2 here. So we can basically take 1/12 out of the brackets, isolate that, or we can also isolate this in h and t. So ht, or h cubed actually, no, h squared, sorry. And then what we left over is h plus 2d. So that's our moment of inertia. So important, it might seem like a very complicated structure that we have to calculate our moment of inertia from, but we realize that moment of inertia is nothing else than the total moment of inertia is nothing else than the summation of the components. So this 1-2 section, we to the 2-3 section. Looks like one. The 2-3 section is directly obtained by 1/12 h cubed t, and then for 1-3 we said is equal to 1-3 is equal to 1-2, and we can calculate that as well. And then at the end, we just summed up the different components. So now we have our moment of inertia. The next step is basically filling out, starting with this procedure what we wrote down here. So we're going to make a cut, we're going to do open sections, we're going to find the correct shear flow. So let's do those steps now. And then the question is, where are we going to go make a cut? As mentioned earlier in a previous lecture, we want to basically do it at around the symmetry point, so we can basically make our life easy. So a cut would be, the best location in this case would be at point 1. So we can calculate 1, 2, or 1, 3, and then 2, 3, and then the rest we can think by symmetry. So we know at the starting point, so QB1, that's of course is our cut, so that's equal to 0. So now let's do segments 1, 2. So QB1, 2, that's equal to our starting point, which is 0, so we ignore that, plus this section. So that's equal to minus sy over ixx. What's that? It's 1/12 h squared h plus 2d. And then we have to evaluate the integral from 0 to s for segment 1, 2, and we multiply by ty ds. So 0 to s, ty ds. So in this case, we already identified that y is equal to, what is that? S multiplied by sine alpha. And we know for S1, that's equal to S1 multiplied by minus h over 2d. So what we can do is just substitute this into here and then do the integral from 0 to d ds. 0 to d. Okay, so we can do that. So we plug these values in. So sy 1/12 h squared t h plus 2d. Now we substitute our new value for y. So it comes from 0 to s t s1 multiplied by minus h over 2d. ds1. So the minus cancels out with this minus. The t cancels out, so we can simplify this to sy. And we have an h here and a 2d, so we get h 2d. And let's see how far we can go. So I'm going to write the t in here as well, so we get h squared t h plus 2d. And then we get 0 to s, s1, ds1. And you always want to do this basically to simplify your life. You can isolate the variables that are dependent on the integral, and then so separate those from the variables that don't vary with the integral. And now we can say, well, this t cancels with the t in the numerator and denominator cancel. And what we can also do is that basically this h can cancel with one of this h, and then the 2d we can take into our, let me see, denominator, right? Yeah. So we can take 2 out of it. And what we can also do is, so the 2d basically goes into here, 2d. The 1 over 12 goes up, so this becomes 12. And then we can divide 12 by 2, becomes 6. So there are a couple of minor mathematical manipulations you can do to get sy, 6sy, and then get hd, h plus 2d to get to this part. And then if you evaluate the integral, of course, this becomes s1 over 2, evaluate from 0 to s1. And of course, our bound is, we go from this segment, it goes from 0 to d, so this segment becomes 0 to d, and s1 squared, by the way. So if you evaluate this, yeah, let's plug actually still s1 in, because this becomes the equation for the segment QB12. Now, before we can start with QB23, we have to evaluate QB12 at S is equal to D, because that's our starting point for segment 2, 3. So QB2 is equal to QB12, evaluated S equal to D. Now we can fill in this equation D, and we can evaluate it. So if you do this, so this 2 becomes 3, this becomes D squared, you have a D here, so you can cancel out 1D. So you get Sy multiplied by D over H plus 2D. And that's our starting point for segment 2, 3. Does this make sense? Good. Also, for those online, if it doesn't make sense, please send me an email. I can go ahead and elaborate more. So next step is calculating segment 2, 3, and 1, 3 we can define by symmetry, because that's equal to 1, 2, but then opposite in sign. So let's keep that on board, erase this, and we can calculate QB 2, 3, which is equal to QB2, that's our starting point, which is this value, minus Sy Ixx, 0 to S Ty ds. In this case, y will vary from, so y goes at point 2 is equal to minus h over 2, and y at point 3 is equal to h over 2. So from this, we can define that y is equal to minus h over 2 plus s2, and s2 goes from 0 to h. Good. So now we can plug it in. Let's plug in immediately. QB23. We had, this is a 3, by the way. We got a 3 here. So we get 3 Sy D over H plus 2D minus, and then what we can do is, we can start with this section, because, nope. Let's see. This becomes 12. The T still disappears. Okay. Yeah, let's start there. So this becomes 12 Sy a bit easier. Let's keep it sy, now xx for now. Let's evaluate the integral. Becomes 0 to s t, and then y is defined as this. So we get s2 minus h over 2. It's still visible. ds2. So this will be the same. Let's evaluate only the integral sy d over h plus 2d minus sy ixx. And then what we get is t, and this becomes s2 squared over 2 minus h over 2 s2. So we can take basically 1 over 2 out of this bracket. So we get 1 over 2 here, and then here we get s2 squared minus h s2, evaluated at 0 to s2. And now we can plug in this, what we had here. So in this case, what will happen is that the thickness will disappear with this thickness here. The 12 goes up, and then over 2, so we get 6. So sy d, h plus 2d. This becomes 6 sy. T will cancel out. So we get, let me see, h squared, h plus, so we get here h squared, and then h plus 2d. And then this remains the same, s2 squared minus h s2, evaluated at 0 to s2. And then if you want to calculate point 3, so QB3 is equal to QB 2, 3, evaluated as equal to h. And if you plug this in, you will get, of course, because of symmetry, you get the same value. So you get 3 sy h plus 2d. So what will happen is this becomes h squared minus h multiplied by h. So it becomes h squared, so this part is 0, so this drops, and you still have your starting value. Which makes sense. Afterwards, it's also very good to do, especially when you have a symmetry problem. Just evaluate, so if this, in this case, segment 2, 3, these are basically our symmetry segment. Evaluate it at the end point, and you should get the same answer as your start point. So if there's something goes wrong, then you probably did, in this part, something wrong here in the integral formulation. So it's basically double check for yourself. Okay. Now we determine our, so we did the cut, we determine our open sections, and now we have to determine our correction shear flow. So while I erase this, can you guys think about what location would be the best to do the correction shear flow equivalence, the moment equilibrium equation or moment equivalence equation around, which point and why?
The shear is flowing to the end point of the triangle. So where you have those two lines at that in that triangle?
Which point? 1, 2, 3.
Oh, 1.
Okay, that's good. So the reason why you should pick 1, as mentioned before. So let's draw our shear flows basically into our segment, right? So we know there's a correction shear flow Q as 0, right? And we must calculate this one. But what are the existing shear flows? Well, we know that this was a positive. So this we defined, we started with 1, 2, went to 3, and then we went to 1. So this was QB1, 2. This is QB2, 3, and this is QB 3, 1. So what we know with the correction shear flow, we said we're going to apply moment equivalence between the external applied shear force and our internal moments due to shear flows. So we said Sy equal to psi must be equal to our QB shear flows multiplied by arm moment arm P over the cross section, so integral around the cross section, plus 2 times the enclosed area QS0. So now if you take the moments around point 1, we see that it interacts with the shear flows in QB12 and QB31 go through point 1. So they don't have an equivalent moment arm. So those become 0. So now the only moment arm that you have to take account for is QB23. So this equation, this part of the equation now is significantly reduced in complexity. You have just one equation, and that moment arm is equal to this distance from this center point to 1. So let's draw that with red. So the moment arm is this segment here. And that segment, so we know that this is equal to D. So we know that this segment L is equal to D cosine alpha. And alpha we already had identified earlier. So we basically have a very simple equation. Okay, so let's write that out. And of course, Sy has the same moment arm L as L. So psi in this case is equal to L. So our equation becomes 0 to H, because that's the segment of our 2-3 section. So we multiply our shear flow by the segment it travels over to get our shear force, and then we multiply it by the arm to the point of interest to get our shear, to our moment. So we get QB to 3 multiplied by moment arm L, and then of course the integral of ds, and then we do enclosed area QS2. Let me see, goes counterclockwise, it's positive. That one's counterclockwise positive, so this is Sy, and this becomes L as well. Okay, so let's identify the enclosed area first. That's an easy step. The enclosed area of a rectangle is half base times height, so it becomes 1 over 2 H times L. So plug this in. 0 to H, QB to 3 multiplied by L, ds, plus the 2.5 cancel, so it becomes HL QS0 equal to Sy multiplied by L. So now we see that actually L appears in all the 3 components, so we can ignore it. So we can basically say divide by L, so the Sy, this becomes H, and this becomes QB ds. Now we substitute in we substitute in QB. Yeah, well, actually, let's isolate the QS0. QS0 becomes Sy minus the integral from 0 to H QB to 3 ds over H.
Why did you take the L's out?
Because they appear in QB times L, that's the moment arm. Here it reappeared or appeared in the definition of enclosed area, and here it also is the same distance towards point 1.
So you just divided by L.
Yeah, so you can divide by L. It doesn't matter. just to simplify your life. And now basically we have to recall with our, let's do it on this side, what our QB23 was, QB23, and that was equal to QB3, was equal to 3 SY D over H plus 2D minus 6 SY, and then we had H squared over H plus 2D, and then S1 2 squared, or segment 2 squared minus H times segment 2. Yeah, it's visible. Okay. So another key point is you have to fill in the shear flow of that segment. So it's always mindful for yourself, it must be a function of an S term in it. So you cannot fill in the start point or the end point. Now, because we take again the integral here in order to get the equivalent moment. So now what you get is, let's isolate Sy over H here. H. Guess a minus. Okay. Sy minus, I thought we could isolate it. And then we get 0 to H. And then we fill in this integral Sy D H H plus 2D minus 6 Sy H squared H plus 2D, and then S2 squared minus H S2 and DS2, and this all over H. Okay, and this is a bracket here as well. So we know this is basically a constant, so we just this integral becomes ds2. This the s2 squared becomes 1 over 3 s cubed. This sh now h s2 if you take the integral becomes h s2 squared over 2. Okay. So yeah, okay. Actually, let's do this. Let's just isolate the integral here. 0 to h ds2. Okay. So this becomes sy d s2 over h plus 2d. And keep in mind we have capital S and we have also subscript small lowercase s. This becomes 6 sy h squared h plus 2d, and this becomes 1 over 3 s2 to the power of 3 minus 1 over 2 h s2 to the power of 2. Okay. And then basically what you can do is let's see. I assume this direction. Because I had a plus here, I have to assume it's counterclockwise. Just a small thing, okay? And what you have to do is just plug in this, evaluate at 0 to h. So with 0, this whole term is 0. And if you take in h into account, what you get is this becomes an h. Let's do another color. So let's say we evaluated at h. This becomes h. This becomes h to the power of 3. This becomes h multiplied by h squared. So this becomes h to the power of 3 as well. So we get 1/3 minus a half. So what we get is, what is this? 2/6 minus 3/6, so it's 1/6. So minus 1/6. So this becomes plus. This drops. So this becomes, see this correctly. So this becomes 1/6, I said. We have the 6 here, so the 6 is dropped. So this becomes an h cubed. H squared can drop, so this becomes an h. Does that make sense? Yeah, so far so good. This h drops here. I made an error somewhere. Let's see. Yeah, we have a D here. Let me double check. That's why this is correct. There's an h squared here, that's correct. And then we evaluate. Yeah, I made this some. So this part is correct. So do the integral, and if you get a correct equation or correct value out of it, what you should get is sy d. I cannot find error very quickly. Is h plus 2d, and there should be a minus here.
So yeah, over there, you said it was counterclockwise, but you drew it clockwise. So does that have something to do with it?
No, this is counterclockwise now. Now the reason why I said I drew it incorrectly is because I used a plus here. Then this all needs to follow the same logic convention. So convention is counterclockwise positive. So this creates a counterclockwise moment, so it's positive. This will basically counterclockwise shear flow, therefore it's also positive.
Yeah, that's clockwise.
If it's about 0.1.
Oh yeah, okay. As long as you're consistent, clockwise. So in this case, I assume clockwise positive. Sorry. Yeah, you're right. Sorry. Yeah, clockwise positive. Because I assume in this case, sy being clockwise, so that one's positive, and then these internally are clockwise, so that's all of them are positive. If I had assumed counterclockwise positive, then this would have been a minus, and minus. Okay. So let me see what I did wrong here. Let me do redate. A couple more minutes. Let me actually finalize the solution. So once we have correction shear flow here, so what we do is, because this is a negative, you just have to be careful where you add up and subtract. So in this case, the final shear flows QS12 will be equal to QB12 minus QS0. QS23 is equal to QB23 minus QS0, and QS31, sorry, is equal to QB31 minus QS0. So you basically just add to it, because there's a negative sign here, you subtract it. So let's revisit this integral, what I did wrong. Let's see. What we can do is, Let's take out some terms that we can take out 3sy over h plus 2d. Then we get here basically d. We get minus 2 over h multiplied by s squared minus hs. I dropped the subscripts for now, so I want to see what I did wrong. So if you do this integral, then this becomes, do the integral and evaluate, so this becomes h dh. This becomes 1 over 3 h cubed. This becomes 1 over 2 h cubed. Is this correct? Yeah. Okay, this becomes h cubed or h squared. This h squared, this h drops. This becomes 2/3 minus 1. So this becomes plus 1/3 h squared. H squared. Now you can divide by h. So this becomes h. Okay. Yeah, there was just a small error, and then you can continue. And then you get, you have to take this s into account. Okay. Will work out eventually. I think I just made a small error, but this solution is valid. And then, like I said at the end, because this is negative, which basically what it means is, in this case, we assumed all to be clockwise. Means that this one is actually counterclockwise. So this, because a negative shear flow means nothing else than the shear flow goes in the opposite direction that you assumed. So then if you look at it, because they go in the opposite direction, you have to subtract to get QB, QS 3,1 is QB 3,1 minus QS0. Here, QB QS 1,2 is equal to QB 1,2 minus QS0. Similar here, QS 2,3 is equal to QB 2,3 minus QS0. To get your final answers. And that would be it. And that would be a good point to start. Okay. I think it's 12:55. So are there any questions? No? Okay, perfect. Like I said, the exam will be posted Sunday. You have 48 hours. Tuesday, 9 a.m. is the deadline. It should take a couple of hours, so there should be more than enough time to do it. Okay, thank you very much, and see you guys next week.